Hello, everybody. I'm Jacob Block. I'm actually you. Hangue will be presenting the second half of the presentation. I'm a researcher at the Petit Bioscience lab. We are developing the tongue drive system, wirelessly operated wearable technology. So our talk will kind of walk through the talk. So we're first going to go over some background and motivation, then specifically what the tongue drive system is and how it works, how we've verified it. So what we're really interested in is improving the quality of life. Improving the quality of life of SCI patients or people spinal cord injuries. So when you lose control or when you damage your spinal cord, you become very dependent on other people. You have trouble getting around the house, trouble going outside on your own, just your dependence has increased. And what we're seeing is a lot of, the numbers are growing in how many SCI patients there are, how many SCI people there are. 11,000 new cases every year. So we're looking to address that and improve their quality of life. So a bit of a background about previous devices. There's kind of classic switch-based systems where the user, it's not for completely immobile people. So depending on where you have your injury, you might still have some control. So that's what these systems are for, where you can still push a button, you can still manage a joystick, but that has limited usage and for a limited audience. There's also head pointers where they put a reflector on your head and you're able to kind of point where you want your attention to go. So kind of if you want to move a cursor on the screen, you can point your head at that location. But those are just difficult to use because you have to maintain control. You can't wave your head. You have to be kind of locked into the system pretty tightly, and frankly, it gets a bit tiring. Another system is the eye tracker. So similar to the head tracker, you physically wear a device that can track where your eyesight is pointing to. It's not as tiring as moving your whole head around, but still you have to maintain this connection to the system pretty tightly. And also it's a weaker signal than just the inherent noise of detecting where your eye is located. It's a noisy system. Then I mentioned joysticks earlier. Again, those systems you need some physical ability to manipulate or use the systems. And then BCI, brain-computer interfaces. These are pretty interesting, but again, it's difficult to use a BCI out in the real environment. They're really cool and being able to pick up brainwaves, but it's a very noisy signal, and you can't really rely on that in a complicated environment. So why use the tongue? So the tongue avoids the whole spinal cord problem. So any injuries below your neck, if you have a functioning voice, you can move your tongue. Actually, you don't have to have a functioning voice, but if you can move your tongue, which most spinal cord injury patients can, then you have this opportunity to use our system. And again, when you speak, it requires very precise motions. It requires precise. You can immediately, without thinking, touch every single one of your teeth with very little effort, I guess. So the tongue drive system is using that advantage. By putting a small magnet on the tip of your tongue, we can track that magnet and turn that into a control system. Actually, so at this point, I think you just wanted to talk more about the details of the system.
Jacob. So here is the first prototype of the control system, which is implemented as a wireless headset. So here is 4 magnetic sensors which can be positioned around the user's cheeks. So it can detect the magnetic field from the magnet on the tongue. Also, it has a wireless communication interface to communicate with the external interface like power wheelchair or the power personal computer. This external headset can be flexibly fit to any size of the head, but at the same time it has a robustness issue in case of when people are driving the bumpy load or the external force is applied. So we developed the intraoral control system which can be fit onto the loop of the user's mouth and also can be tightly fixated onto the upper teeth. So it can be well protected inside the mouth. Also, it can provide more privacy for the user not to be seen as a disabled. This is the actual implementation of the intraoral control system which was implemented as a dental retainer. So every electronics are integrated into the small printed circuit board, and this printed circuit board along with the battery and the charging cord is hermetically sealed with the paraffin or silicone and molded inside the dental acrylic, inside the dental retainer. One more thing I need to note that this cannot be charged through the exposed electrical connection, so it should be charged through the wireless interface. Here is the overall system block diagram. The small signal generated from the magnetic sensors are amplified and digitized and transmitted through the dual band wires, and the RF receives the low magnetic data and converts it to the specific user's command, use the smart signal processing algorithm, and delivers it to the personal computer or power wheelchair to drive the wheelchair or to navigate the mouse cursor on the computer screen. This is the actual implementation of the receiver, which is called also as a universal interface because it interfaces with the other potential applications. So it is implemented as a small white box which can be easily put onto the desk or can be fixated onto the power wheelchair. So it has a wireless interface to communicate with the intraoral control system, and also it can charge the intraoral control system inside the small box. And then I will show you how it works. Our biggest enemy is the Earth's magnetic field because our system is using the magnetic field. But fortunately, this Earth's magnetic field works as a common field for all four magnetic sensors. So the magnetic sensors can receive the pure magnetic field signal from the tongue magnet by cancelling out the Earth's magnetic field. And then the signals are amplified, digitized, and wireless transmitted. And then the receiver converts the sensor data to the specific command using this reconstructed 3D space. So this well-separated dot shows how well the commands are separated. So using this reconstructed 3D space, the tongue drive system can recognize which command need to be issued according to the position of the tongue. Here is the system verification via clinical trials. Our first clinical trials was conducted at Shepherd Center in Atlanta with 13 subjects with high-level spinal cord injuries, and they successfully drive the navigation route with the power wheelchair using our tongue drive system. Our second round of clinical trials were conducted both at Rehabilitation Institute of Chicago and also at Shepherd Center in Atlanta. At the second round trial, we have a more well-organized experimental setup. The first experimental setup was a computer access test, which includes the horizontal tapping, vertical tapping, and central tapping, which is known as a famous Pislow test 2. to measure how fast the tongue can issue the commands. Also, we have the virtual navigation task to see how well the users can drive the power wheelchair using our tongue drive system. So people can just move their tongue right to turn right, and move their tongue left to turn left. Here is the result of the experiment. You can see there is still a gap between the keypad and tongue drive system. However, the performance of the tongue drive system improved significantly through the 5 sessions. Also, this virtual navigation result shows that at the 5th session, subject reached to the perfect range for completion time, which means that performance is mainly limited by the maximum speed of the power wheelchair rather than the lack of control. And I will show that there is also special applications for tongue drive system. Tongue drive system can be used where there is a holder for use their hand or foot, like a military application or space application. So we hope the tongue drive system can be used as a third arm for even for the normal able human. Thank you for listening.